need to look again. I can't read. I know they need to use Faraday's law of induction for it, right?
Right. Yeah. We'll talk about that later. All right, good morning, everyone. Welcome back from Halloween. Hopefully you kept some brain cells left. That'd be great. Anywho, so I just wanted to know what we talked about last time. So we talked about a loop of wire and an external magnetic field. And we said is that this thing feels no force, but it does feel the torque, but the torque then is equal to the magnetic moments crossed by this external magnetic field, where the magnetic moment is equal to N, which I didn't write down last time, but it's a generalization what we did write down, where N is simply equal to the number of loops, because each loop would have exactly the same amount of torque on it, which means I'd sum all of those together, which means I would just multiply the total number of loops. Times the current times the area vector, where again the area vector is a vector which points perpendicular to A. Oh, so points perpendicular to an area. So again, it either points in this direction or in this direction. Just depends on the actual direction in which we choose, which in this case is chosen by right-hand rule number 3, which says we choose the direction then of the area / the magnetic moment by number 1, curling our fingers in the direction of the currents, and then number 2, our thumb then points in the direction of the magnetic moment. And then this has a energy associated with it as well, where that energy is something equal to a negative the magnetic moment dotted then by the external magnetic field. So again, it has exactly the same structure as the electric dipole in an electric field. Good. So that's about as far as we got last time. So today we're going to do a couple examples of this. So the first example says, determine the magnetic dipole moment of an electron orbiting a proton in a hydrogen atom at a given instant, assuming that it is in the ground state with a circular orbit of radius 0.529 times 10 to the minus 10 meters. This is what's known as the Bohr radius. So it's in the ground state, i.e. it's in its Bohr radius. So in this case, we're going to look at the planetary model of the hydrogen atom. So Bohr's planetary model. So let's look at the planetary model. Let's do our example. So here we have a proton. Here's my proton. And then around this, I have my electron. So here's my electron. And we're going to say this is the planetary model. So this thing is orbiting at a fixed radius. This is my fixed radius, which was told it's a problem. The radius is equal to 0.529 times 10 to the minus 10 meters, which is the same thing as 0.529, what's known as an angstrom, which is what's called the Bohr radius. Right. So what I want to know in this case then is simply, let's say, what's the magnitude of the magnetic dipole moment created by this scenario? So right, so what's going to happen? So remember that the magnetic moments, at least the magnitude of this guy, is equal to, in this case, the number of loops times the area times the current. But in this case, I simply have one loop because I have one electron which was going around here. So in this case, n is equal to 1. So I know my magnetic moment then is going to be equal to simply my current times my area. Now in this case, the electron is sweeping out a circle of radius r. So what is the area? Pi r squared. So this is going to be equal to the current times pi r squared, which means all I have to do now is determine, well, what's the current? So remember, current by definition is change in charge divided by the change in time. So let's go ahead and look at the current. So we know the current then is going to be equal to the change in charge. For my change in discharge, in this case, is simply going to be the charge in electron, because that's the only thing that's going around. And then the change in time is the amount of time it takes to go from this point all the way around back to this point. But how much time is that by definition? That's a period, right? So in this case, we know this guy is simply going to be equal to the charge of the electron divided by the period. So the next question is, well, what is the period? So we need to know what the period is. So let's think about the period. So as we talked about before, we know that 2 pi times the radius is equal to the velocity times the period, which in this case means that the period then is going to be equal to what? 2 pi times the radius divided by the velocity. So this is my period. So now what I need to know then is, well, what is the velocity? So how are we going to get the velocity? Well, we're going to get the velocity by the fact that we know this thing is going around the proton with a constant speed, which means that it's going to have some sort of centripetal acceleration. So we know that this thing is going to have an centripetal acceleration. So it's going to be pointing towards the center. So this is B. AC. And then from this, we can actually then get the velocity by using Newton's second law. So we can then say, well, the sum of the forces acting on it is then equal to the mass times the centripetal acceleration, or that's the same thing then as mass times the velocity squared divided by the radius is then equal to the sum of the forces. Now, the question then becomes, what's the force? So what is the force which is holding the electron in orbit around the proton as it oscillates around it in uniform circular motion? So meaning we have basically three choices. We have gravitational force, we have the magnetic force, or we have the electric force because there's no strings or springs or anything like that. So we don't have to worry about tensions and stuff like that. So these are our three options that we have. So it's either going to be the gravitational force, it's going to be the magnetic force, or it's going to be the electric force. Which one do we think?
Magnetic.
How many want to say magnetic? You're all by yourself. Or all by yourself.
Why would that not be two forces? That
Oh, well, that's a great question. There's actually a whole bunch of forces acting. But one of them is dominant over the other.
Okay.
And I'll tell you, it's not gravitational. Because if it was gravitational, then the distance between the proton and the electron would be like the distance from here to California. That would be the size of an atom. And it's gravitational. If it was purely gravitational. Thank God it's not. So it's on a much smaller distance than that. But it's not gravitational. But it's technically a whole bunch of other forces. There is gravity associated with it, but gravity is such a small component to it, so it doesn't really matter that much. So then, before I answer that other question, so again, how many want to go with magnetism first in? What are we looking for? What's the other option? Electric, right? So it turns out it actually is electric. So the primary dominant force, which is actually holding this thing into its orbit, is actually electric force. Now, magnetism is in there, but magnetism is actually small corrections to the ground state energy of the electron. So this is actually what's known as the spin-orbit coupling. So basically what happens is the proton has a magnetic moment, the electron has a magnetic moment, and then the interaction between these two magnetic moments, which is what's known as the spin-orbit coupling, gives you corrections to the ground state energy, which is what causes the ground state energy to split into multiple energies, because if you didn't have that, the ground state of the electron in the hydrogen atom is actually what's known as fourfold degenerate. There are 4 different states that all have exactly the same amount of energy. But due to the spin coupling, this is what's known as the hyperfine splitting. What happens in that case is you have 1 true ground state, and then you have 3 that are all the same energy, which is what's known as the triplet state. So the overall answer is there's all kinds of different contributions. But on top of that, there are also other things too. There are relativistic contributions. There's what's known as the Darwin term and all kinds of other different things. And I told you way too much. So anyways, the point is what holds it actually in orbit is dominantly the electric. So it's actually the electric attraction between the positive and negative charges.
I guess I'm a little confused because why wouldn't it just linearly go to the proton?
Oh, that's because just the same reason why the moon orbits around the Earth. It's all because of its linear momentum. So in this case, since it has velocity in this direction, this thing is radially infalling towards it, but this velocity carries it so that it stays exactly at the same distance away. Again, in the planetary model. So it's all because of its linear velocity that carries it, so it doesn't actually collide into it. But yeah, if I had just an electron with a proton and this guy was stationary initially, it would take about the time frame of about a pico to a nanosecond for it to crash into the proton, which means we'd have no life anywhere. No planets, no anything, because all atoms would be destroyed in less than a picosecond. I'll just look at it. Okay. It's okay. So good. Let's go back here. So we know the only force acting on this thing is the electric force. So let's go with the electric force. Great. So this has to be equal to our mv squared over r. So in this case, we know the electric force by Coulomb's law is going to be K, which is our favorite K value, 1 over 4 pi epsilon naught, times Q1 times Q2, but each one has the fundamental charge. So this is going to be E squared divided by the radius r squared, then is equal to mv squared over r. Okay, so just remember that our electric force equal to magnitude-wise K Q1 Q2 over R squared, but in this case Q1 is equal to Q2, which is equal to the fundamental charge. This R cancels with one of those, so from this I can then solve for the velocity. So this gives me then K E squared over MR square rooted is then equal to the velocity. Okay. So now I'm just going to plug this into this expression, which means I'm going to take 1 over that and plug that in. All right. So this is going to be the same thing as, let me erase this because we already know that. So from here, I'm going to get my tension, my period is going to be 2 pi times R times the square root of that MR divided by KE squared. So this is then my period. If I want, I can move this R on the inside, which would make that guy a cubed. So this guy's going to become equal to 2 pi square root of MR cubed divided by KE squared. Okay. So now we can go all the way back to this beautiful expression here. So now we know the period is, so this is going to be then E times the period, which we need 1 over the period. So we're going to get a 2 pi on the bottom. And we're going to get a square root of KE squared all over MR cubed. So this is then my current. All right. Finally, for my magnetic moment, now I know my current. I'm simply going to multiply that by pi r squared to find then my magnetic moment. So finally, it's going to become E divided by 2 pi square root of KE squared over MR cubed times pi r squared. So this is then my magnetic moments. From here, I can cancel then things out, right? So I can cancel pi's out from here. I can pull out an R from here, which would cancel that guy, but I'm just going to leave it. Or I can bring that R squared on the inside and get an R to the 4th. Well, let's not worry too much about it. So again, we know what R is, we know what E is, we know what K is, we know all these different things. If we plug in our numbers, what we find is it should work out to be 9.27 times 10 to the minus 24. Let's write that down. So it's going to be 9.27 times 10 to the minus 24. This has units of amps meter squared. Go back. I got hyper. Okay. Let's do another example. So my next example says 6. I don't like it moving up there. Okay, it says we have a coil carries a current of 2 amps in the clockwise direction when looking down the y-axis, is parallel to the xz plane and has 3 turns in an area of 4 times 10 to the minus 3rd meter squared and lies at a uniform magnetic field given this way. Okay, so let's kind of draw what's happening. So in this case, do it like this. My next example. So let's say for funsies, this is my X, this is my Y, and this is my Z direction. So what it's saying is that I have a loop of wire, which is actually 3 loops of wire, where if I'm looking down in the Y direction, in this direction, I see the loop carrying current in the clockwise direction. Okay? So what that means is that it's going to be doing this. This is the direction of the current. So if I was looking at it from a front view, so let's say my eye is here looking at it, what I see is this is my positive Y direction. So I see my current doing this around in the clockwise direction. Okay? So that's what this picture on the right hand side is. Now what also does this tell me? It also tells me that I have an area where that area then is equal to, what was it? 4 times 10 to the minus 3 meters squared. 4 times 10 to the minus 3 meters squared, and that it has a current I, which was equal to 2 amps. and it's in an external magnetic field, which was given by 2 minus 3 minus 4, 2i minus 3j plus, is it plus or minus 1? Minus 4. Thank you. Minus 4k.
Maybe around.
Millitesla. I'll take a look at it. It's negative. Good. So what it wants to know then is, what is the orientation energy of the coil in the magnetic field? So I'm looking for what's the potential energy, and then what is the torque in unit vector notation on the coil due to the magnetic field. Good. So what I want to know in this case then is A, what is the magnetic energy? So what is the magnetic potential energy of this thing being inside of this coil? And then part B, what I want to know then is, what is the torque? How much torque does this guy actually feel? What's up?
Just a quick question.
Sure.
What's the difference between like how you would write potential energy and then magnetic moment or strength? Because they're both used, right?
The magnetic moment. Oh, so magnetic moment is mu. It's the Greek symbol, right? And then this guy is u. But soon we're going to look at energy density, which is little. So not to confuse you too much. Right. But yeah, so technically magnetic moment is the Greek symbol mu. So that's why it has a little tail on front. I'll make it a mu. But yeah. And then energy, potential energy is always capital U. So first things first, let's go ahead and look at the direction of our magnetic moment. So we know that the magnetic moment, by right-hand rule number 3, we're going to curl our fingers around in the direction of the currents, which means it's going in this direction. So our thumb would point along that way. Or if I use this guy, my fingers would curl around in this direction, my thumb would point in this direction, which means the positive y is pointing this way, it's then pointing in the negative y direction. So in this case, my magnetic moment then is into the page, which means my magnetic moment is then going to be equal to negative the current n times the current times the area in the j hat direction. And in this case, we're told that n is simply equal to 3. Right? So we have 3 coils in this case. So let's go back to our question. So that's what it says here, has 3 turns. So in this case, n is equal to 3. Good. So for this, all we want to do then is take our dot products and our cross products. So for A, we want to know what is the magnetic energy. Well, we know our magnetic energy is then equal to negative the magnetic moment, dotted then by the magnetic field. So this guy then is going to be equal then to a negative of a negative n times I times A in the I hat direction, dotted then with, so there's going to be a Bx in the I hat direction plus By in the J hat direction, plus Bz in the K hat direction.
What is that? Why is the first one in I hat direction?
Oh, sorry, J hat. I think I said J hat, but wrote it I. Thank you. Now remember, dot products tell me what's parallel to what. Is J parallel to I at all? No, so the dot product between those is 0. Is J parallel to K at all? No, so dot product between those is also 0. Is J parallel to J? Yes, so dot product between them is simply equal to 1, which means it's going to pick out simply the J portion. So this is then going to be equal to a positive NIA times then By, all times J dotted with J, but again, Dave dotted with J is simply equal to 1. Okay, next part is now we're just going to put in our numbers. So it's going to then be equal to 3 turns times my current, which was 2 amps, times my area, which was 3 times 10 to the negative 3 meters squared, times my magnetic field, which was then equal to negative 3 milliteslas. Right, so our milliteslas, we would just have to simply turn into teslas, which is 10 to the negative 3. Plug in the numbers we find in this case then is that our energy works out to be negative 7.2 times 10 to the minus 5. Negative 7.2 times 10 to the minus 5. What's that?
It's not 4 times 10.
Which one? The area? Maybe. Just going off my bad memory. You were absent. Good. I said the answer is 7.2. So negative 7.2 times 7 minus. Okay.
What do you
Yep.
have the negative 3?
So negative 3 comes from the B. So in this case, we're looking at the Y component, so that's negative 3 milliteslas. That's where the negative 3 comes from. Or I can write this as negative 72 microjoules. It'd be the same thing. Okay? What's up, Homer?
Why is the first one why is it when you do a cross product you have a J hat the first one? I'm not like, oh never mind.
Okay.
I'm actually curious now. I kind of like that question.
A cross product?
Well, how do you get the first?
Oh, so like a band comes back to our picture. So we know that this thing is orbiting around the J direction. So again, right-hand rule number 3 says I curl my fingers in the direction of the current. My thumb would then point in the direction of the area or the magnetic moment, which means this is only along the Y direction, and that's pointing in the negative Y direction since the positive Y direction is this one. That's where the negative J comes from. Good. So let's look at the torque. So we now know that torque is then equal to the magnetic moment crossed then by the external magnetic field. So again, this is going to be equal to what? N times like negative NIA J hat crossed then by, so it is Bx in the I hat direction plus By in the J direction plus Bc in the K hat direction. Now again, remember, cross product tells me what's perpendicular, which means is J perpendicular to I? Yes, so that's non-zero. So let's write out that one. So it's going to be equal then to negative NIA Bx. And we're going to get a J crossed by I. Good. Is J perpendicular to J? No, that's parallel, so that cross product gives me 0. And then is J perpendicular to K? Yes. So then I'm going to get a negative NIA BZ J cross K. Now, if I want to know the directions of these guys, remember if I have I, J, and K, if I go from I to J, that gives me a positive K. If I go from J to K, that gives me a positive I. And if I go from K to I, that gives me a positive J. If I go in the opposite direction, I simply get a negative sign. So here I'm going from J to I, which means we're going this way, opposite direction. So I'm going to get a negative K. So this first one is going to give me a negative K. And then here, if I go from J to K, that gives me a positive I. So this one then is simply going to be a positive I. So plug these in. So it's going to give me a negative NIA times, I'm going to get a negative Bx in the K hat direction plus Bc in the I hat direction. Bx we know is positive, that's simply equal to 2 millitesla. Bz we know is negative, so that's going to be a negative 4 millitesla. So a negative sign here and a negative sign here is going to kill off this negative sign, which makes the whole thing positive. And when I plug in my numbers, what I find in this case then is that my torque becomes, you can read that, that's 9.6 in the I hat direction plus 4.8 in the K hat direction, all times 10 to the minus 5. So this is here. So this was 9.6 I hat plus 4.8 K hat. Go. All times 10 to the minus 5. It says units of Newton meters. Remember, joule is a Newton meter and a torque is a Newton meter, but again, a torque is a vector, which is why we call it a Newton meter, not a joule. So even though the units are technically the same, they stand for two different quantities, so they have to have different. Okay? All right, so one more topic to talk about for today. We're going to talk about what's known as the Hall effect. Talking about the Hall effect. So the Hall effect was the experiment that told us if it was an electron or a proton, i.e. a negative charge or a positive charge, which was actually moving in a wire. So we had current moving through a system. Again, remember thanks to Benjamin Franklin, and we thought it was actually positive charges, but it was this experiment that told us it was actually negative charges. So let's describe this experiment. So how does this experiment work? Well, basically what we're going to do is we're going to take a flat piece of metal. So let's say here's my flat piece of metal. And I'm going to line this thing along some particular direction. So let's say this is my X direction, just for funsies. Then let's call this then our Y direction. And then in this direction is going to be our Z direction. So let's say this thing has a width to it. This is my width across here. This also has a thickness. So this distance across here is going to be its thickness. Let's call that T, where this is thickness, not time. Also going to have a length to it. So let's call this distance across here simply its length. Now, from here, what we're going to do is we're going to put this in an external magnetic field. We're going to allow that external magnetic field to point perpendicular to the direction of the current, which is going to flow through this thing, which in this case, I'm going to put in the Z direction. Okay? So my magnetic field in this case is going to be uniformly pointing in the Z direction. And then we're going to go ahead and run current through the system. We're going to have current, say, running in this direction. So it's going to be the direction of my current. So in this case, my current's going to be flowing in the positive X direction. So what's going to happen? What's going to happen is, remember, current is simply charges. My charges inside of here are going to be moving if they're positive charges in exactly the same direction as that of the current itself. So let's say for now I have positive charges, or I have Q, which is greater than 0, all moving then with a drift velocity. That drift velocity will be in the same direction as my current. Right? So it's going to be my velocity. So what's going to happen? What's going to happen is what? I have now a charged particle moving in an external magnetic field, which is perpendicular to the direction of the external magnetic field. So we know these things are going to feel a force. The direction of force then will be, I have to point my fingers in the direction of the velocity, which in this case would be out towards you. My magnetic field is upward, which means I'm going to rotate my palm upward towards the external magnetic field, which means my thumb is pointing in this direction, which is then in the negative Y direction. So these guys are going to ultimately be deflected in the negative Y direction, which means this guy's going to feel a force, a magnetic force, pointing then in the negative Y direction. So what's going to happen? So what's going to happen then is what? As this guy is moving in this direction, it's going to feel a force, which means all of these guys are going to curve, and they're going to curve and start building up on this wall here, which is on the Y is equal to 0 location. Right? So what's going to happen then? They're going to start building up a whole bunch of positive charges along this wall. I'm going to get a bunch of positive charges. But if I have a negative charge, what are my negative charges going to do? They get repelled into this direction, which means at the same time, I'm going to build up a whole bunch of negative charges on this wall. But now if I have positive charges on this wall, negative charges on this wall, what do I develop inside of the piece of metal? I'm going to get an electric field, right? So what I'm also going to build is that I'm going to have an electric field, which is going to point in this direction here. So this is going to be my electric field. So I'm building up positive charges on this side, negative charges on this side, which means I'm going to point in an electric field. But now I have a charged particle sitting in an external electric field, which means what's it going to feel? An electric force. What's going to be the direction of the electric force? Well, in the direction of the electric field, because it's a positive charge, which means the direction of the electric force will be opposite to that of the electric or the magnetic force, which means this guy's going to feel the force in this direction. So it's going to be my electric force. So what's going to happen? Well, initially, this is going to be a very big force. I have no electric force. I'm going to build up all these forces, or all of these charges over here, build up the charges over here, create an electric field. The electric field is going to create an electric force. The electric force is going to get bigger and bigger and bigger and bigger over time until eventually what's going to happen? What would happen? the forces are going to be the same, right? Exactly. So what'll happen is this electric force will keep increasing until eventually the magnetic force equalizes that of the electric force, which means the net force on these guys is going to be 0, which means all these charges are going to start to flow in a straight line again. Okay? So eventually what's going to happen is that the sum of the forces acting on these objects, on these charges, will then go to 0. In this case, this is going to be the sum of the forces in the y direction. So here I'm going to have the electric force then minus the magnetic force is then equal to 0, which means the electric force is going to be equal to the magnetic force, which means we're going to have the charge then times the electric field, then it's going to be equal to the charge times the velocity times the magnetic field times sine of the angle between the two. But again, the velocity is in the x direction, magnetic field is in the z direction. What's the angle between those two things? 90 degrees. Sine of 90 is equal to 1, so the sine portion goes away. So in this case, the q's are going to cancel. So I'm left with then that the electric field is equal to the velocity times the magnetic field. This thing is effectively a velocity selector that we talked about last night. Now, what happens though is if I have an electric field across the two sides of the plate, what else do I have? I have a width, I have an electric field. So what do I have a difference between here and here? A potential difference. So what ends up happening then is I create a potential difference, which is what's known as the Hall EMF. So we're going to call that a Hall EMF. So it's a potential difference, which we're going to call an EMF, which is what's called the Hall EMF. So what I want to do then is relate this electric field then to this Hall EMF. Remember, the way I do that is that the electric field is equal to the potential divided by the length, which in this case is simply equal to the width. Because in this case, the electric field is equal to a constant. So it's going to be equal then to my Hall EMF divided by the width. So in this case, I have my Hall EMF divided by the width, that is equal to the velocity times the magnetic field, which means my Hall EMF that I create across here, then is equal to the velocity times the width times the external magnetic field. So this is what's called the Hall EMF. So what happens is by running this current through this strip of metal, I'm going to create a potential difference between these two sides that I can measure. Okay. Now, what would happen is what? If I took my voltmeter and I put one wire here and I put one wire here, if I have positive charges moving, what's going to happen then is this is going to be my 0 volt side. This would be my non-zero volt side. So in this case, I'd measure a positive potential difference between the two sides, if it was positive charges moving through the wire. But if it's a negative charge moving through the wire, what's going to happen then is the opposite is going to happen. The negative charge is going to go to this side, the positive charges are going to go to this side, which means my voltmeter is going to tell me a negative potential difference because this is now my high side, this is my low side, and I'm measuring this as the low side, or measuring this as the high side, and this is the low side. So the point is, if it's actually negative charges moving throughout the wire, I'm going to get a negative potential difference instead of a positive potential difference. And this is exactly what happened. So what happened when Hall et al. Set up this experiment, they were looking to see what direction they would actually get the potential difference. And what they found was that all the positive charges were on this side, negative charges were on this side. So they got a negative potential difference, which meant it was actually negative charges moving throughout the wire, not positive charges. So this was the experiment that actually determined absolutely it was negative charges which were allowed to move throughout the wire, not positive charges. Therefore, current is actually negative charges moving, not positive charges moving. So this is called the Hall effect. So good. Hall effect is used for all kinds of different things as well. You can use this in blood, for example. This is one way you can measure what type of blood you have, if it's positively charged, negatively charged, etc. You can also measure the velocity of the blood moving inside of a vein, for example, using the Hall effect, i.e. the direct velocity here. So you can look for things like obstructions, so too much cholesterol in one particular area, which would get a blockage. So if you have a blockage, you're blocking, right? You're gonna have a stroke, basically. So you can use a Hall effect for all kinds of different things, but the major thing it was used for was to determine the direction, or at least what was moving, positive charges and negative charges. So great, now we know about the Hall effect. Let's do an example. So this says we have a long copper strip, which is 1.8 centimeters wide, 1 millimeter thick. is placed in a 1.2 Tesla external magnetic field, which is perpendicular to the direction of the wire. So it says when a steady current of 15 amps passes through it, the Hall EMF is measured to be 1.02 microvolts. From this, we want to determine the drift velocity of the electrons, the density of the free conducting electrons in the copper. So good. So let's talk about all these things. So what do we know? So our example. So we know that we have a current of 15 amps. We have a magnetic field magnitude, which is equal to 1.2 Teslas. We know we have a width, which was equal to 1 point something. 0.8 centimeters. We know we have a thickness, which was equal to 1 millimeter. Good. And we know this guy is simply equal to copper. Finally, we also know the Hall EMF that we measured was equal to 1.02 microvolts. So from all of this, we want to determine A, what is the velocity, i.e. the drift velocity, my drift velocity. And then B, we also want to know what is the number density. So how many charges per unit volume do I have? So let's look at part A. So part A, we now know that's what the Hall EMF is equal to the width times the velocity times the magnetic field. So in this case, we know Hall EMF, we also know the width, we also know the magnetic field. The only thing we don't know is the velocity. So let's solve this for velocity. So my velocity then is going to be equal to my Hall EMF divided by the width times the magnetic field. So it's going to be 1.02 times 10 to the minus 6 volts divided by the width, which was 0.018 meters, times magnetic field, which was 1.2 Tesla. Right. Look at my numbers. What I find in this case then is 4.7 times 10 to the minus 5 meters per second. So this is my velocity or my drift velocity of the electrons moving through. For B, we now want to know the number density. So let's talk about the number density. So part B, we want the number density, right? So going back to what we did last exam, we know that either the magnitude of the current density is equal to the charge times the number density times the drift velocity, or we know the current is equal to the charge times the number density times the drift velocity times the area. In this case, we don't know the current density, we could find it, but we know the current that's given to us in the problem, so we might as well use this definition because we just found the drift velocity, we just simply called it velocity. These two things are the same. So from here, we can easily find this for the number density. So in this case, we're going to have the number density then is going to be equal to the current divided by the charge, where these are fundamental charges, these are electrons moving, so we know the charge in this case is equal to the fundamental charge. The velocity from our previous slide times the area. So the question now becomes, well, what is the area? Because going back to our picture, we technically have multiple areas, right? We have this area here, we have this area here, or we have this area here. So what area do I care about? Well, times the thickness, right? What we care about is the direction the current is flowing through, which means the area we care about is this area here, which means our area in this case, A, is going to be the width times the thickness. Good. So let's plug that in. So it's going to be equal to the current divided by our fundamental charge times the velocity times the width times the thickness. So in this case, plug in the numbers. This was 15 amps divided by 1.602 times 10 to the minus 19. That's my fundamental charge. Times my velocity, which was what, 4.7 times 10 to the minus 5? Times my width, which was 0.018 times my thickness, which is 0.001, because that's 1. Did I remember the velocity right? Yes. Not as old as I thought. Okay. So plugging in, what I find is then 11 times 10 to the 28th. So my number density then ends up being 11 times 10 to the 28th per meter cubed. Yeah, let's see a point there. So it's gonna be... That's it. It's okay. Per meter cubed. So 1/meter cubed. Or you can write it this way. So this would also be 11 times 10 to the 28 meters to the negative. Either one of those is sufficient. What's up, Omar?
What is that last number that you plugged in?
Oh, that was the thickness, which was 1 millimeter. So that's 0.001.
Oh,
Can you move over?
Sure. So from here, I got a whole bunch of group assignments for you. I was hoping to have more time, but Omar just dropped me.
I have a question.
Sure.
So when you're solving for, and
Yep.
where was the first equation? Where did it come from?
Which equation?
The first equation that you wrote.
This one?
Yeah.
This was one of the ones we learned from last exam.
Okay.
This was relevant for question number 2. Last exam. So this was derived there. We derived these two things simultaneously. First, we got this one, but we also know that current by its definition, or at least current density, I should say, is equal to the current per unit area. So that's how we went from this one to this one. But that came from last chapter. So that's taken as a known at this stage because we already derived it before. So that's where that came from. That's when we were doing chapter 27. Okay. So let's at least briefly talk about some of these group assignments. I'm going to give you more time to work on them, but that's fine. Let's talk about a whole bunch. So the first ones have to do with magnetic force. So this one says we have an ion source is producing lithium-6 ions, where each one has a charge of positive E and a mass that's 6 times the mass of the proton. So it says the ions are accelerated by potential difference of 10 kilovolts and passes horizontally into a region where there is a uniform vertical magnetic field, which is 1.2 Tesla in magnitude. What is the magnitude of the smallest electric field to be set up in the same region so that these ions pass through undeflected? This is simply a velocity selector question. So in this case, you have the velocity selector, you know what the velocity is, that's based off of this potential here. So this part you're just using conservation of energy that we used way back when with exam number 2. We know the magnetic field, we know the velocity from here, so you're just looking for the electric field. So that's all we're doing in this one. So question number 1 here, let's roll that down. So for group assignment 1. So in this case, you have potential region. This is 10 kilovolts. So here you're taking your lithium-6, accelerating this guy to come out with a velocity of v. So you have to find first your velocity of v. And then from there, you're setting up your velocity selector where you know that it has a magnetic field, where the magnetic field in this case, let's say it's pointing inward. The magnetic field is 1.2 Teslas. And what you're looking for is the electric field here that's going to cause these lithium atoms to pass through with exactly the same velocity that's coming through. So we found for velocity selectors, the velocity has to be equal to the ratio of the electric field to the magnetic field. And here you're using conservation of energy. The change in kinetic energy plus the change in potential energy is equal to 0 to find the velocity. So there's conservation of energy. Okay. Not too bad. Look at the second one. So the other one then says we have a charged particle moves into a region of uniform magnetic field. That's magnetic field region here, where we're told the magnetic field is pointing outward towards you. This guy ends up going through a semicircle here in this direction. And we know that it takes a time of 130 seconds for this thing to go, or 130 nanoseconds for this thing to go through this circular region. So first thing we want to know is what type of particle is this? Is this a proton or is it an electron? So we have to use our right-hand rule to determine if it's a proton or an electron. From there, depending on the sign, if it's a positive sign, we're going to use the proton. If it's a negative sign, we're going to use the electron. And then from that, we're trying to then determine what is the magnitude of the magnetic field. Right? Then part B, we want to know if the particle is sent back through with a magnetic field the same, but twice the previous amount of kinetic energy, how much time does it spend inside of the region? So we're keeping the magnetic field the same, but we're increasing the kinetic energy by a factor of 2, which means you're increasing the velocity by an amount of the square root of 2. How much time does it spend inside of the magnetic field region? The answer is 130 nanoseconds. It's exactly the same amount of time, regardless of how fast it's going. Kind of talked about this on Friday, but I'll let you guys kind of work that out. So this one's not bad. It's a nice, easy one. Right-hand rule kind of stuff. Cool. So that's those two. Then we have this one. Thank you. So it says we have 10 loop wire, that's this thing. So there's 10 loops here. Has in a uniform magnetic field region and carries an current of 2 amps. The loop is free to rotate about these axles here. So basically, here is my loop. This thing is free to rotate like this about the central axis here. Over here, I have a mass of 50 grams, which hangs on the edge of this thing. So what I have is 50 grams hanging here. This thing wants to rotate, which means I have a gravitational torque pulling it, wants to rotate this way. But we want to know what's the strength of the magnetic field so that this thing ends up with a magnetic dipole moment, which is going to create a torque in the opposite direction to rotate this thing back so it stays exactly flat, horizontal in this field. So I've got a magnetic torque pulling in this direction. I want to then hold gravitational torque pulling this way. Magnetic torque I want to pull in this direction to then keep this thing so it's completely flat. So I want to know in this case then, what is the size of the magnetic field required to do this? All this means is that magnetic torque has to equal the gravitational torque. So for this one, the third one, in this case, I'll make group assign it 3. What I want in this case then is that the sum of the torques acting on this object is equal to 0, which means that I want the magnetic torque to then be equal to the gravitational torque. So I just got to use torques, magnetic moments, definition of torque, all that kind of good stuff. So that's our third one. Okay?
I'm assuming since no dimensions were given on the loop, that somehow cancels out.
Oh, I think I gave dimensions. Let's go back to the picture. I thought there were supposed to be dimensions. Yeah, let me check another picture and see if I have dimensions. But otherwise, if I don't give you dimensions, then yeah, assume that it's going to cancel out. But I don't think it's going to at this stage. But yeah, let me look at my master one and then I'll let you know from there. And then I got one more for you. This is the Hall effect problem. This is basically identically the same problem we just did, just different numbers. So in this case, we now have a current of 3 amps instead of 15 amps. This thing has runs lengthwise, has a width of 1 centimeter instead of 1.8 centimeters. It's 4 centimeters long, and then has a thickness of 10 microns instead of 1 millimeter. Has a hole potential of 10 microvolts instead of 1.02 microvolts, and is in a magnetic field of 1.5 Teslas instead of 1.2 Teslas. But otherwise, it asks all the same questions. So all you're doing is exactly the same problem. So all those equations that we wrote down, just basically recopy them down, put in new numbers. So exactly the same question. And that's it. So Dan did great on time. So sorry to give me enough time to work on these things, but oh my God, later, or at least I need. Mark, any questions about the So anyways, have a good day. I'll see everybody on Wednesday. So Wednesday, we're going to start magnetic field calculations. How do we actually determine magnetic field? We're going back to doing integrals and all that good stuff. I saw your email. What do you want to talk about? Okay. Sounds good. Send me your schedule and then we'll go from here.
Yeah, also, I'm not flexible.
Yes,
I think this is said it's you, what is it, okay?
well, for the class.
Yeah, I get it, I get it. Yeah. My
Those are
bad.
not bad questions.
No, they were great questions.
Just
Just a little derailing from your exercise.
because
That's
I don't understand why they were.
Oh, there's all kinds of other forces there. There's also quantum mechanical forces and all kinds of stuff. But yeah, that's not weird.
So my first question is, I don't understand this cross product, like how do you get,
Oh, so that's not equals there to there. So that's an extension of this guy.
oh, so that you actually add.
Yes,
Okay,
correct. So I went equals here, but I ran out of room to write it over here. So that shouldn't have an equal sign there. That should just be part of that. Right.
just be a plus sign.
Yes, plus a negative, all that good stuff. Yes.
So that means, then you just distribute
So then I just use, right, so this, so, and they all had the NIA, so I pulled that out. And then from here, I end up with a BX or J cross I, and then here I have a BZ, J cross K. But then J cross I is negative K, and then J cross K is positive I.
And for this, would you ever have it? I don't think you'd ever have a parallel of more than one side, if that makes sense.
Well, you could, it depends on the orientation of the moment. But in this particular case, the answer is no, because the moment's only pointing along one direction.
Okay.
But if, for example, if I gave you that coordinate system, but then I said the moment was in the X and Y direction. So it was the superposition between X and Y, then in that case, then it would be more complicated.
Okay,
So in that case, the dot product would be okay, but when you're doing the cross product in that case, then you would want to use the more general one that we wrote down in terms of components. Because then trying to do all this stuff out would be a little more nasty, but we're good.
okay, okay,
But yeah, so it all just depends on how I set up the moments.
okay.
But then I can also rotate a coordinate system to make it along an axis, so. What's up?
I was just thinking about that too, so I
Sure.
understand the K mod, I can calculate on that.
Yep.
But I just didn't know which one to like decide to choose out of it, like the J's and the I's, and things like that.
What do you mean, I decided to choose?
Well, like, I know, cause like they canceled the J's.
The J only cancels with the J's.
Yeah,
That's it.
so like,
So here, all I'm doing is I'm doing regular, what you would do as, you know,
you just
distributed.
didn't do like the determinant bars.
Yeah, I didn't do any of that because in this case, I had a three-dimensional vector multiplied by a one-dimensional.
Okay,
So determining, you know, how the cross products work is a lot easier in this case, just to kind of foil it out. Right? So here, all I'm saying is I have some
oh, so you
number.
just went through and
Exactly.
like.
So
Oh,
here I just
okay.
have A times B plus C plus D.
Okay, I was making it much harder than that.
Yes.
Okay, thank you.
You're welcome. Yeah, so as long as I have a single one-dimensional vector, it's easier to kind of do it that way
Yeah,
than try to actually set up the entire